Welcome to section 4.2. 4.2, we're going to take a look at something called Rolle's theorem, and then we're going to take a look at something called the mean value theorem. They're connected. That's why they're in the same section. We only have two objectives: understand and use Rolle's, understand and use mean value theorem. So we'll start right away. Just hop right into Rolle's theorem. All right, so Rolle's theorem. First off, remember the extreme value theorem. The extreme value theorem states that for a continuous function on a closed interval, it's what we were looking at in 4.1. It's going to have both a maximum and a minimum value on that interval, and that both of these values could occur at endpoints. That's the extreme value theorem. Right? What Rolle's theorem does is Rolle's theorem gives us conditions that guarantee the existence of an extreme value not on the endpoints, but it forces it to be in the interior. So extreme value theorem, which is essentially section 4.1, said this. If you've got a continuous function and you put it on a closed interval, then somewhere on that closed interval is going to be a highest point and a lowest point, an extreme value. But the extreme value theorem allowed for the extreme values to occur at one or both of the endpoints, for a max and or a min. What Rolle's theorem does is Rolle's theorem gives us the conditions that are necessary to guarantee that that extreme value happens not at one of the endpoints, but somewhere in the middle. And when I say middle, I don't mean a plus b divided by 2 middle. I mean somewhere between a and b, in the interior of the closed interval. Okay? All right, so here's how Rolle's theorem works. If a function f is continuous on a closed interval a to b, and you can take the derivative, that it is differentiable on all values between a and b. And if, so this is the third and, f of a is equal to f of b. That means that whatever value the function starts at on the left-hand edge of that interval, it ends at on the right-hand edge of the interval. Then, so there's three ifs. If it's continuous, and it has a derivative, and the starting y value and the ending y value, f of a and f of b, are the same, then there has to be at least one x value somewhere between a and b at which the graph has a horizontal tangent. Right? So here's an example of a function that meets the definition of Rolle's theorem. Right? Here's our closed interval a to b, and this function is continuous between a and b. I can draw the whole thing without picking my pen up. There's no sharp corners or any weirdness to it, so I could find the derivative for any value in there. And because the starting point, that is the f of a value, and the ending point, that is the f of b value, are the same. For whatever reason, they decided to call it d in their picture. If that is true, that is that f of a is equal to f of b, then somewhere between a and b, in this case we're calling that letter c, you're going to get that horizontal tangent line that we've got right there. And in this case, for this drawing, that would be a relative maximum. Right? Well, what if it went the other way? And what I mean by that is, for some value a and some value b, where the f of a was equal to the f of b, what if the graph went down? Well, then it would have to come back up, and then there'd be some value about there-ish, where the tangent line would be horizontal, and we would call that value c. Right? I want to point out something, though. Right here, it says there must be at least one x value. What does that mean? Well, what if our graph, instead of just being a simple little up-down or down-up, what if our graph wiggled? Then I'm going to get a horizontal tangent here, another horizontal tangent here, and another horizontal tangent here, 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 and here. And so instead of having one C, I'm going to have a C1, a C2, and a C3. And if I made it wiggle more, could I make it have more of these C values? So we can have one C, we can have many C's. Right? It's just, all Rolle's theorem does is it says, if some conditions are met, we can guarantee that we will have an extreme value, whether it's a max or a min or potentially both, somewhere in the interior. Right? When the differentiability requirement, though, is removed, you could still have that extreme value somewhere in the interval, but it won't yield a horizontal tangent. So something like this. This function is continuous on a closed interval a to b because I can draw it without picking my pen up. It still has the f of a equal to f of b business here. And it still has a maximum somewhere between a and b at the point we're calling x is equal to c. But Rolle's theorem doesn't tell me that this has to happen because this function is not differentiable on the entire interval a to b, the open interval, right? And so it could happen. It doesn't have to happen, though, when you relax that definition of or that requirement of differentiability. Okay? The requirement of differentiability helps us because it forces it to have a horizontal tangent at that maxes or mins, okay? To go up, to come back down, and to go back up again and get those horizontal tangents that we like. And so that's why Rolle's theorem has that requirement to it. Right? So a couple different situations that could occur. You could have something incredibly boring like this, where this is your function f. It's continuous, it's differentiable, and actually it's going to be equal to 0. The derivative f prime would be equal to 0 for all values between a and b, which means that every single point on that interval is an extreme value in the sense that they are all the highest and consequently they're all the lowest. But let's be honest, this is very boring. It's a horizontal line segment. It doesn't really have much interest. It doesn't really have much application, so that's not one we're really going to look at. What we're really talking about is things like this, where we have a function that has a starting point, f of a, an ending point, f of b, it's continuous, and it's differentiable everywhere, and that means that somewhere it's going to have a value c such that f prime of c is going to be equal to 0. And that f prime of c is equal to 0 is going to yield either a maximum or a minimum. Remember, just having a derivative equal to 0 doesn't mean you're a max, or doesn't mean you're a min. It just means that something important happened there, a horizontal tangent, and you are an extreme value. Okay? Here's the example of a couple of c's, where we have a function that starts at the right place and stops at the right place. That is, the y values are the same. Goes up, goes down, goes back up again, and we're going to get two c values where f prime of c1 is equal to 0, as well as f prime of c2 is equal to 0. Now, I hope that you're kind of looking ahead and seeing where this is going to go. Again, another one here. This one is the down and then up. It's the flip, if you will, the vertical reflection of that guy right there. Right? All right. So I'm hoping you're seeing where this is going to go. Rolle's theorem is going to go here, where we're going to be asked to not just find those extreme values, but find the values of c that make this true. Okay. All right, so let's go back up here real quick and just take a look at Rolle's again. What are the requirements? Okay. So let me clean some of this mess off of here. Okay. There are three requirements. 1, it must be continuous. 2, it must be differentiable. And 3, endpoints must be the same y value. Then there's going to be at least one x value, those numbers we're calling c's, where it has a horizontal tangent, and saying it has a horizontal tangent is the same as saying that the derivative at c will be equal to 0. All right, so here's our example. Find the two intercepts and show that f prime of x is equal to 0 at some point between the two x-intercepts. Now, why on earth is this in the section on Rolle's theorem? Well, let's take a look at what we're working with here. We have a function, and we're supposed to find the two x-intercepts. Well, if a function has two x-intercepts, that means it's going to have two values, f of a and f of b, where both f of a and f of b are both equal to 0. So that's that third requirement of Rolle's theorem, The first two are that this thing is continuous and this thing is differentiable. And then if all three of those are true, then at some point between those two intercepts, you're going to get that horizontal tangent. Now, I know that at least one person out there is thinking, yeah, but what if the graph goes the other way? Well, what if it goes the other way? What if it's a opening down kind of like this? It's still going to have those two intercepts. They're still going to have two values where it's equal to 0. And then if we can show that it's continuous and differentiable, it's going to have that horizontal tangent. We're going to be able to find that value C. Right? So first things first, I need to make sure that those three requirements are being met. Requirement number 1 said it must be continuous. Well, f of x is a polynomial. So is a polynomial. And those are continuous on the interval negative infinity to positive infinity. So we're good there. So any interval, any a, b that you give me is going to be part of infinity to negative infinity. So it's going to be continuous there. 2, f prime of x, the derivative of a polynomial, is also a polynomial. So it will be differentiable on that negative infinity to positive infinity. So we're good there. Right? Now we just need to figure out what the heck a and b are to give us our interval so we can make number 3 be true. And number 3 is that f of a is equal to f of b. Right. Now to find a and b, they want us to find those two x-intercepts. So the first thing I'm going to find the x-intercepts by taking my function f of x, which is x squared minus 3x plus 2, and setting it equal to 0. Right? Now, this looks like it's a factorable quadratic, so I'm going to factor it. I think that's x minus 2 times x minus 1, right? And we factor it so we can use the zero product principle. And I get the two values x equals 2 and x equals 1. So that means that my a must be 1 and my b must be 2. So I'm looking at the interval from 1 to 2. Definitely continuous there because it's continuous on all real numbers. Definitely differentiable there because it's differentiable for all real numbers. And f of a is equal to f of b because f of 1 is equal to 0 and f of 2 is equal to 0. So all three necessary requirements are met. And so now what I'm going to do is I'm going to find the value c. I'm going to find c, which is going to be an element of my open interval 1 to 2 such that f prime of c is equal to 0. Well, before I can find c, I got to find f prime. So what is f prime of x? Well, derivative of x squared is 2x, derivative of negative 3x is negative 3, and the derivative of 2 is 0. And now I will take that derivative, set it equal to 0, and figure out where this is going to happen. Let's see, that's when x is equal to 3 halves, or if you prefer 1.5. Is 1.5 somewhere on that interval? I believe it is. Now, here's something to keep in mind. When I do this algebra right here, is it possible, maybe not for this one, but for some other function, that I might find several answers? Not just one value where it's equal to 0, but several values where it's equal to 0? And if I find several values where that derivative is equal to 0, then what I'm going to have to do is I'm going to have to make sure that I don't make the mistake of including in my final answer values that don't really work. Right? The only numbers that I should be getting are numbers, in this case, between 1 and 2. And so if I had worked this problem out and I had gotten two answers, one of them was 1.5 and one of them was 4, well, I would keep the 1.5 because it's on the interval that I care about. But what would I do with the value 4? Well, I just simply throw it away because it's not on the interval that I care about. It's a solution to the equation that I set equal to 0, but is not a solution to the problem because I'm only supposed to be looking for answers between 1 and 2. And so I've shown that it works because it is a polynomial that is continuous on the entire real number line. Its derivative is also a polynomial, so its derivative exists, or is differentiable for all real numbers. F of A is equal to F of B. I found A to be 1 and B to be 2 by taking the function and setting it equal to 0 because it told me to find those x-intercepts. And then I took the derivative, set it equal to 0, because Rolle's theorem says it will be, and found out when that was going to happen. In this case, it happens when x is equal to 3/2, which is smack dab in the middle of 1 and 2. And that makes sense. Okay? If I think about what this function is, the original function f of x, appears to be a parabola opening up. And if it's a parabola opening up, or opening upwards, if you prefer, and it crosses the x-axis at 1 and 2, I'm looking at something like this. Say that's 1 and that's 2. I'm looking at a parabola that does that. And so then there's going to be my horizontal tangent, which is the vertex of the parabola. And I'm hoping you remember from college algebra that the vertex of a parabola is always halfway between the x-intercepts, provided that your parabola does cross the x-axis. If you happen to have one of those sneaky parabolas that doesn't cross the x-axis, well, if it doesn't cross the x-axis, you can't use this trick. Right? All right, moving right along. Let's take a look at another one. Oh, wait. We're already at 16 minutes, so I'm going to stop this video, make another one for part 2 of this, and we'll do a couple more examples.